In this video, we want to look at right triangle trig. So we want to focus on, for today, right triangles. And most of what we're going to talk about you have seen before, and so this would not be anything that's completely new. We're just going to connect it with what we've looked at. So what we're going to look at today is SOHCAHTOA. And I know you've seen this before, and if you remember, what this stands for is sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And this depends on where your angle is, right? This will be different if your angle's in a different spot. Now, also, this only works for a right triangle. This does not work for any triangle. It only works for a right triangle. And so we only do this for one of these two angles. This does not work with the 90-degree right triangle as we do this, okay? So we want to think SOHCAHTOA. So I know you've seen this before. Let's look at some examples, how we can use this. So let's say we have this triangle. This is a 3, 4, 5 Pythagorean triple triangle. Here is our theta. So sine is opposite over hypotenuse. So that would be 4/5. Cosine is adjacent over hypotenuse. That would be 3/5. And tangent is opposite over adjacent. So that would be 4/3. I'm not sure what happened with the rest of my tangent there. But that would be 4/3. Now, let's say we have a triangle where we don't know one of the sides. To find this missing side, we would have to use Pythagorean theorem. So if I would call this side x, we would say that x squared plus 5 squared equals 13 squared. And if we solve that, we would get x is 12. Just like 3, 4, 5 is known as a Pythagorean triple, 5, 12, 13 is a Pythagorean triple. That just means that is a triangle where the sides are all nice integer values. Once again, right triangle only. So sine, now we've moved our angle. So now sine of theta is opposite over hypotenuse, so that's 5 over 13. Cosine of theta is 12 over 13, and my tangent's missing again there. Tangent of theta would be 5 over 12. So it has to do with where your angle, where your theta is on what is your opposite, adjacent, or hypotenuse. Here are the angles here, so the 5 is the opposite. Back here, my angle is up here, so 4 is the opposite. And if you pay attention to these Pythagorean triples, you'll see these a lot. They really like these on the ACT. So they will have, 3, 4, 5. That's a very common one. However, you can also do multiples. So like you could say 6, 8, 10. You could say, let's multiply by 4, 12, 16, 20. Those are all Pythagorean triples. I like to use those on things like ACT because you get nice whole numbers. Now, let's say we are given a triangle and they tell us that angle or cosine of C is 8 over 14. So that means for angle C, the adjacent side is 8 and the hypotenuse is 14. So one of the things we'll start to talk about as we do more of these, when we have this side, we use capital letters to signify the angles of a triangle, and we use lowercase letters to signify sides. So this would be 14 squared is 8 squared plus c squared, and if we do that, we get c to be the square root of 32. Which that tells us that the sine of C, opposite over hypotenuse, is the square root of 32 over 14. Now, one of the things I want to think about here with this is consider if we do the sine of B. So angle B is up here. So the sine of B, opposite over hypotenuse, is 8 over 14. The cosine of B is the square root of 32 over 14. So notice when you're dealing with these right triangles, there's these angles that are known as cofunction identities, that this sine equals that cosine. And this cosine equals that sine. And you know angles B and C have to add up to 90, right? Because of the right triangle. So if I just pick a random angle and I'll use degrees, that would tell me, I don't even know what the answer is here, whatever the sine of 20 is, that would equal the cosine of 70. Because sine and 70 and all come from the same triangle, and it's just opposite angles of the triangle. Now, sine, cosine, tangent are only 3 of our angles, or our trig functions. We have 3 more that we want to look at. So our first one is secant, and secant is equal to 1 over cosine. Cosecant is equal to 1 over sine, and cotangent is 1 over tangent. Now, let me just explain a little bit of why we use these, okay? We're not going to, and so you don't need to know why this is, but you understand we use them. But if you remember back, we talked about the difference between like a function and its inverse function, right? This represented the inverse. It was not an exponent, it represented the inverse. We also talked about this when we did matrices. This was the inverse matrix, right? Not reciprocal. This is not an exponent. Well, the problem is if I have this, people could get confused about, do I mean the inverse of sine or do I mean 1 over sine? So to avoid this confusion, and we're not there yet, but if we look at the inverse sine, we're going to write it like that. And actually, we would put an X there. Okay? That is on the calculator. When you see this right here, above sine, this inverse sine. That's inverse sine. If we have 1 over sine, we are not going to write that as a -1 exponent. Instead, we write this as cosecant instead of dealing with negative exponents for sine functions, and it just avoids confusion. So that's why we have all of these. So let's go back to here. And let's say we want to look at secant, cosecant, and cotangent. So if we know cosine is 3/5, we know secant is 1 over 3/5, which that is just equal to 5/3. So secant's just the reciprocal of cosine. Cosecant is the reciprocal of sine. Cotangent is the reciprocal of tangent. So these are our 6 trig functions. As you do some homework problems, it will say find all 6 trig functions, and this is what we mean by the 6 trig functions. So we have some identities here then that connect with this. So first are known as our reciprocal identities, which just say this. Just like we defined, cosecant is 1 over sine, secant's 1 over cosine, cotangent's 1 over tangent. Sine, would be 1 over cosecant. We're just kind of rewriting this formula. Cosine's 1 over secant, tangent's 1 over cotangent. And finally, if you think about it, sine times cosecant is 1. Because if you have sine times cosecant, which is 1 over sine, you can see that equals 1. Our other properties or identities that we're looking at here today is tangent and cotangent. Now, yes, tangent is equal to opposite over adjacent. But we could also write tangent as sine over cosine. So let me go back to our original triangle here and think of tangent not as just opposite over adjacent, but think of it as sine over cosine. Sine is 5 over 13. Cosine is 12 over 13. When we divide fractions, we flip and multiply. That would cancel and give us 5 over 12. So you can see these quotient identities are another way we can write sine and or cotangent, tangent as just sine over cosine. That sometimes helps us out, and makes things a little easier to make calculations and do work. The last thing we're going to look at here today is what are called our special triangles. Now, these special triangles, you talked about them in geometry. And we're going to use our numbers a little bit different than what you used in geometry. I'm going to assume most of you don't even remember what you did in geometry, so I'm not even going to compare it to what you used to do. I'm just going to show you what we are using here. So for us, both of our special triangles, our hypotenuse is going to be 1. Okay, that's different than what you did before, so if you remember these at all, that's why it's different. Now, for our 30 degrees, pi over 3, so that, if you remember, pi over 3 is 60 degrees. So this could be pi over 6, pi over 3, pi over 2. Or it could be 30, 60, 90, whether we're degrees or radians. The side opposite the 30 is 1/2. And the side opposite the pi over 3, or opposite the 60, is square root of 3 over 2. Now, if you have a pi over 4, pi over 4, pi over 2 triangle, or 45, 45, 90, obviously this is an isosceles triangle, so the two sides are the same, but if our hypotenuse is 1, the side of both triangle is square root of 2 over square root of 2. So, if you wrote those down in your notes, we want to think about how we could use those to just kind of answer the next couple questions. So think about this triangle here. 60-degree triangle. Think about what angles and what sides, I've given you all the possible options here, to fill this triangle out. I'm going to pause for about 30 seconds and let you try that to find all the sides and all the angles, and then we'll come back and talk about it. Okay, we know the hypotenuse is always 1. We know this is 60, so that tells us this angle here is 30, but we don't have a 30, but we have a pi over 6. Now we know the angle opposite the pi over 6, or opposite the 30, is 1/2, and the side opposite the 60, or pi over 3, would be square root of 3 over 2. So we just want to know and make sure we understand those. Let's try another one. Same type of thing. Find the angles, find the sides. Give you a second. I'll give you 15 seconds to fill this one out. Once again, hypotenuse is 1. This is 45, then this angle's pi over 4, or also 45, and that makes each side square root of 2 over square root of 2. Now, how do these special triangles help us? So for right now, how can we use these special triangles? Well, if we know we have one of these special triangles, we're able to evaluate what is cosine of pi over 6. What is cosine of 30 degrees? Cosine is adjacent over hypotenuse. But because all of our special triangles have the hypotenuse at 1, our cosine just becomes the adjacent side. Sine of pi over 6. Opposite over hypotenuse, but the hypotenuse is 1. That just becomes the opposite side. So by knowing these special triangles, it allows us to find the sine and cosine very easily from the triangle. So what would sine of 30 degrees? Given the triangle, pi over 6 is 30 degrees. This is 1/2. This is square root of 3 over 2. So that is going to be how we are able to use this. Now, if we want to find tangent, we could say either that's sine over cosine, or we could say that's opposite over adjacent. Either way. And cosine, you see here, the flip and multiply, 2's would cancel, and I get 1 over the square root of 3. All right, let's talk about how we can do these on the calculator. Okay, first off, on your calculator, one of the most important things when you're evaluating these on the calculator is you have to make sure you know what your mode is. So you can go down in here and change your mode from radians to degrees, and that's very important. You are in the right mode to find the correct answer. So if we would go back here, and we want to find the sine of pi over 6. We are in radians, so we need to do radians, pi divided by 6, and we get 1/2. Now, if I do the sine of 30, that also should be 1/2. But because my calculator is in radian mode, I don't get that. If I change my calculator to degree mode, now I get the right answer. Now, from something we looked at the other day with degrees, minutes, seconds, there's a way you can even override that. So let me show you that. If I have my calculator in radian mode, so sine of 30 is the wrong answer. If I would go in and do sine of 30, but then I go to angle and I put the degrees sign there, I am telling the calculator, hey, I don't care what the mode is, I want this to be degrees. That will work. Likewise, if your calculator is in degree mode and you want to use radians, you can go to angle and put the little R there. Now, here though, you have to be very careful because right now that's going to give me a wrong answer. The reason is the calculator is only converting the 3, not the pi. So if you want to do this, you have to do the radians in parentheses and then do the R to get it to still not work. Oh, I did 60 degrees. I'm sorry. That's right. Why is that not right? That is why I'm in degrees. I did the sine of 60 degrees, not the sine of 30 degrees, pi over 6. That was my mistake there. So you have to be careful your modes. So the way I like to do this is I keep my calculator in radians, most of the time, because we do a lot in radians. And then if I want to put the degrees sign there, if I want to say cosine and I want degrees, I will hit angle and put the angle there instead of changing my mode. Now, if you remember, while we're here, let's talk about our cofunction identities. We talked about how the sine and cosine of 20 and 70 are the same thing because they add up to 90. They are the opposite of the triangle. If you remember, we wrote that back here somewhere. Oh, I did it the opposite. I did sine of 20 and cosine of 70. I did it a little bit backwards there, but the same idea holds true. Okay. So if we wanted to try to evaluate these on our calculator, this is a matter of just typing them into the calculator and making sure sine, cosine, tangent, and are you in degrees or radians. The one thing I will mention, if we wanted to find secant of 1.43, now that's radians because it doesn't have the little circle there. There is nowhere built into the calculator to find secant. What we have to do is we have to think of this as 1 over cosine. And if we wanted to evaluate this on the calculator, we'd have to do 1 divided by cosine of 1.43. There is no secant, cosecant, or cotangent built into your calculator. And the last thing is the cofunction, which I've already mentioned, how the cosine and sine of 70 or cosine of 50 and 40 have the same thing. So if you just subtract from 90, those values are the same. All right, you are now ready to do the homework. 5.2, right triangle trig.